Hello everyone and welcome to Sky Scholar. Today we are going to continue with our experimental studies relative to Kirchhoff's law in the infrared. Kirchhoff's law states that given thermal equilibrium, the interior of every cavity is filled with black or normal radiation, which depends exclusively on temperature and the frequency of observation, while being independent of the nature of the walls. With this in mind, let's have a look at what cavities actually contain. We begin by considering holes drilled into graphite or metal blocks as shown in this picture, with copper on the left, then followed by graphite, brass, and aluminum. The blocks were placed in a styrofoam container such that dry ice could eventually be added. In order to make the cavities, we once again used the method provided by DeVos for building a cylindrical blackbody and drilled holes which were 1/4 inch in diameter into the blocks. This time, however, the holes had different depths corresponding to just the dimension of the cone produced by the drill bit, then to a depth of 1/4, 3/4, and 1¼ inches deep. Our experiment starts at room temperature in thermal equilibrium. Note that many of the non-graphite holes have features in them demonstrating that they are not filled with black radiation, despite the fact that the graphite holes already are. This demonstrates that Kirchhoff's law is false. Then I bring my hands towards the blocks. Of course, now the holes are being challenged. We are no longer in thermal equilibrium, but can ascertain the origin of the radiation which is filling the holes. Note how the graphite holes do not change, except for the one which was made from the tip of the drill bit on the right. Note also that the reflection of the radiation produced by my hands helps us to visualize the graphite holes, as thermal photons are now partially reflected off the graphite surface. Then we repeat the test with the heated steel rod. We notice that the left two graphite holes are not affected, while copper, brass, and aluminum holes all get filled with radiation from the rod. Next, we repeat the experiment, but with the blocks surrounded by dry ice. However, while they are being cooled, the blocks are not fully at dry ice temperature and not in thermal equilibrium. However, they will give us some information. Note that now the holes from graphite are always easily seen, as photons from the room are striking the cold surface of the block. The signal to noise in this image is also substantially improved. Again, note how the non-graphite holes get filled with rod radiation, but the graphite holes on the left are stable. Finally, we place the blocks on a hot plate, much like is done in sophomore physics classes. Such experimental proofs of Kirchhoff's law could never claim thermal equilibrium, but they are accepted because people never questioned what they were witnessing. If you heated deep cavities on a hot plate in physics class, they all became identical, and you were told that the radiation was independent of the nature of the walls. As such, we set the hot plate to an adjustment of 5. The infrared camera reveals that this corresponds to a temperature of about 580 degrees Fahrenheit on the hot plate surface. Note that we see crescent shapes in many of the holes, demonstrating that they are becoming filled with radiation from the hot plate. Again, only the graphite holes are unaffected by such patterns, and perhaps the very deepest holes from copper, brass, and aluminum. That was the point of DeVos's paper. You have to make the holes deep in order to ensure that the radiation appears diffuse. But this is nothing more than a cheap magician's trick. With the exception of graphite, the cavities are not producing the radiation, they are reflecting it, as this experiment proves. The radiation they contain belongs to the surroundings and is independent of the temperature of their walls. Clearly, not all cavities are filled with black radiation. In these experiments, only graphite could do work and control cavity radiation. It is evident that when a reflecting cavity is heated on a hot plate, the radiation is simply not produced by the holes, but by the hot plate itself. That is why some of the holes have patterns in them when they should be black. Of course, when the experiment is usually done, the holes are made very deep to ensure that any radiation incident into the cavity from the surroundings will become diffuse and appear as though it was a property of the cavity. However, by using the shallow holes, we were able to ascertain the true origin of radiation in these cavities. Except for graphite, the photons are coming from either the room itself, the heated rod, or the hot plate and entering the reflecting cavities. Hence, the radiation is a property of the surroundings, not of the cavity, as Kirchhoff claimed. Note also that when shallow graphite holes were filled with black radiation, the reflecting holes were not. This again demonstrates that Kirchhoff's law is false, as the only determinant of blackness needs to be the dimension sufficient to overcome diffraction. Once the graphite holes perform correctly, the reflecting holes must do the same in order for Kirchhoff's law to be valid. I hope that you enjoyed this video demonstrating that Kirchhoff's law is without experimental support. If you did, please leave a like. In addition, subscribe if you want to journey with me through space here at Sky Scholar. Comments are always welcome down below, and I'll see you soon on our next video.